For our final lesson in related rates, we're going to look at circles and spheres. Steps 1 through 5 outline our strategy. I've also included in these notes important formulas of area of circles, perimeters of circles, surface area of a sphere, and the volume of a sphere. Starting with example 1. You're going to be asked to work with the volume of a sphere. You're going to be given information about that, and it's going to relate to you taking the derivative of the volume formula. Again, remember, any variable is going to have an associated derivative component. So what do I mean by that? Well, when I read through this example, first of all, the volume is increasing by 50 centimeters cubed per second. This information is telling me that the change in volume over time is 50. At what rate is the radius increasing? When the radius is 4 centimeters. So this is my actual R value. Okay? If I start with the volume formula, what I'm going to do first is I'm going to rewrite this so you recognize that 4 pi over 3 is actually the coefficient of the R cubed variable. When I take the derivative of this, which is what we've done in all the previous lessons, we've taken our formula and taking the derivative, I've gotten dv over dt equals the coefficient out front times the power times that derivative component that I mentioned for the R variable. These 3's are going to cancel. So ultimately, dv dt is going to equal 4 pi times r squared times dr dt. Now we know that pi takes on a value of 3.14. So dv dt is an unknown, r is an unknown, and dr dt is an unknown. Based on the given information in the problem, I can plug in a 50 for my dv dt, positive. My r, they said, is 4. And I'm solving for dr dt. That is my unknown. Okay, so in this case, if I'm going to isolate dr dt, I'm going to multiply both sides by 4 to the third pi. Solving gives me positive 0.29 in my calculator. Centimeters per second is equal to my dr dt, which answers the question of the rate that the radius is increasing. Now, as I move down to the bottom, the second example is going to talk about area. The area of a circle is going to be decreasing at a constant rate of 211 square meters per minute. So my dA dt, it's decreasing at negative 211 meters squared per minute. That is my rate. Okay. Again, if I start with my area formula, pi r squared, and I take my derivative, looking at this, I have 3 unknowns, dA dt, r, and dr dt. Okay? At the instant when the area of the circle is 81 pi square meters, if I look at this formula that I've derived, I have nowhere to put in the actual area. I need r. So I'm going to do a quick separate calculation for a moment in time when the area is 81 pi, knowing that this is pi r squared. Both pi's cancel, r is equal to 9. So in order to fill in for what my r is, and this is not r prime, this is r to the first power, I had to do a separate calculation taking the area and converting back to find the actual radius. Now I can come back to here. So remember, I used this information here in order to determine this r, which is now going to feed into here. And I'm going to say negative 211 is equal to pi times 2 times 9 times dr dt. Dr dt is equal to negative 3.73 meters per minute. One of the patterns that should have emerged over the last 3 days is that we're going to take a geometric formula, we're going to apply our derivative rules, then we're going to substitute in. We need to be aware of how many unknowns are in that new derivative and be able to use the given information to fill in all but one of the unknowns, which we are ultimately solving for. That is a clear part of the process that we are trying to accomplish by doing these problems.